Hi, and welcome to this lesson about oscillations in our simple harmonic motion topic. And today we're going to focus on how we use the equations for something that is oscillating. So just to remind you, in previous sessions, in previous videos, we saw that things like a pendulum, something swinging back and forth like this would engage in simple harmonic motion as it wobbled back and forth. Or something that was maybe secured at a point on a spring, some form of mass. If that was set to bounce up and down on the spring, it would engage in simple harmonic motion. Simple harmonic motion is that idea that if an object is displaced away from its equilibrium point where displacement is zero, if you pull it so it's further away from that point, then there will be a force pulling it back. And if you lifted it up so it was higher up, there would be a force pulling it back. So it would always accelerate towards the middle. In other words, it would, if you pulled it down like this, go bounce, 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 until the energy from the system had been lost to the surroundings and it would come to rest back at the equilibrium point. So we can use equations that describe this motion. So in engineering, this is extremely, extremely important. For example, car suspension works on an idea of springs. Well, if you have suspension in your car, you'll know that when your car goes over a bump, the wheels go bump, bump down into the little hole. But if it's a good car, then the car is quite a smooth ride. So something is quite clever in car suspension that allows it to do the bump, 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 but not to carry on doing something that you don't want in cars, which is, imagine if you went over a hole in the road and you went bump, 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 bump. Be like one of those cool cars that Snoop Dogg might have ridden in back in the 90s. So how car suspension works is using the mechanics of simple harmonic motion. And that's one example of how this works. So the idea with today's lesson is we're going to be looking at the way that these variables change with respect to time. Displacement, velocity, acceleration. Amplitude is a constant for one oscillation because it's the maximum displacement. Time, we talked about how we're looking at how these things vary with time, and we have another constant which is angular frequency. So let's just have a little think about one system that's oscillating, and because we were chatting about it earlier, we might think about a mass on a spring bouncing up and down it goes, mass on a spring. Like I said, this is an important one in engineering for anything that oscillates. If you saw the Dragon X space launch at the weekend, you notice that there is a point during the launch where the engines are going full throttle, and then they throttle down. In other words, they turn the engines down a little bit, and the reason they do that is because there comes a point when the whole rocket will start to oscillate. And to ease the amplitude of these oscillations and any damage it might cause to the rocket, as the rocket goes through that particular speed at which it oscillates quite violently, they reduce the engine's power, and then having gone through that speed, then they increase the rate of acceleration again. So this has got so many real-world applications. Well, here's some very simple equations that we use for this oscillation. And the first one is that x equals a cos omega t. So I've got an equation that relates x to the time. That's the amplitude, that's the angular frequency, which is a number. Or we could have v equals minus a omega sine omega t. The minus, of course, means it's in the opposite direction. So if my displacement were in a positive direction, then my speed would be negative. Then acceleration is equal to minus a omega squared, cos omega t. Now these three equations predict the way that the thing will oscillate as time progresses. So if this guy omega is annoying you, I call him omega because it's the Greek letter omega. It looks a bit like a W, but it's a little bit more bubble, like bubble writing W, but it's the Greek letter omega. Then what we can do is we can have a look at what it actually is. Well, the simplest way to think about omega is omega equals 2 pi divided by the time period, as in the time it takes to do one oscillation. Now this equation, and this is Mr. Clift's top tip to you in the whole of life, this equation is the most useful equation in the oscillations topic. Once you have the time period, you know omega, and look, omega appears in all equations. So you can work out almost anything once you have omega, this angular frequency. And because time period is equal to 1 over the frequency, I can always also write that equation as omega equals 2 pi times the frequency. So both forms are very, very useful, although experience tells me that I tend to use this one more than the others. These are all in the chapter in your book, and the graphs showing the variation of displacement, velocity or amplitude are also in the book. So let's try one problem using these equations. So here is one of the problems that we're going to do today. From the textbook, page 323, we're going to do the questions at the end of this chapter. Now I've chosen question 3 because I think at this point the questions start to get harder. You might find the early ones easier to do. And I'll show you how I'm going to do this particular problem. In this question we're told that there is an object that's oscillating. It completes 20 oscillations in 16 seconds and the amplitude of the oscillation is 0.16 meters. We want to know the displacement at t equals 0.40 seconds. So the way that I'm going to do this is the first thing I want is omega. To get omega, I want the time period. Now the time period is the period for one oscillation. Well, if you do 20 oscillations in 16 seconds, then the time of one oscillation is going to be 16 divided by 20, or 4 over 5, or 0.8 seconds. Great. So I now have the time period for the oscillation. Once I have the time period for the oscillation, I can work out omega. So omega is equal to 2 pi divided by 0.8. And there is omega, and I have it. Now to find the displacement, we use the equation displacement equals A cos omega t. So let's substitute the numbers in that we have. I want to know x. A is the amplitude. There it is, 0.16 multiplied by the cos of omega, 2 pi over 0.8. So I'm leaving in that form for now because it saves me having to round off because it's got pi in it, so I'd have to round off if I wrote the number, multiplied by the time. Well, I want to know the displacement at 0.4 seconds, so multiplied by 0.4. Okay, now you can see this is now just a matter of putting the numbers in my calculator, but for people who are not so familiar with this particular style of problem, the calculator must now be in radians. So I'm going to put my calculator in radians in order to work out the answer for this problem. Now, if you're not sure how to put your calculator into radians, and apologies for people who do know how to do this, here on the very classic school calculator, I use Shift, Setup, and I'm given a prompt for a menu, one of which is rad for radians, and you'll see the little letter at the top of the screen change from D for degrees to R for radians. Of course, if you need it for your mathematics later, don't forget to change your calculator back into degrees. So here you can see that if I put this in, this becomes 0.16 multiplied by the cos of pi, and pi, if it's in radians by the way, is 180 degrees. Cos of 180 is -1, so the displacement is minus 0.16 metres. Now before we get too mathematical, what does that mean? It means that the object has gone through half a cycle. From being at one side of the oscillation, it's gone through the middle and it's out the other side. Because the displacement is the same size as what it started at, but is in opposite sign. From positive to negative means it's now on the other side. It might be oscillating up and down, or side to side, it doesn't really matter. But we can see that we are half a time period in. And that's how I am using and applying these equations. Now today in the lesson, I'm going to get you to do a series of activities that will involve you thinking through and applying these equations for yourself. Okay? Thanks very much.